Today's topic is interference and diffraction. Later on, we're also going to talk about something called scattering, and we're going to talk about lasers. But why are these two topics together, interference and diffraction? And that's because they usually occur together. And this is going to be the topic of your lab, by the way. Back in the unit on waves, we defined interference as when two waves wind up at the same place at the same time. They interfere with each other. And they could do this constructively, where the amplitudes combine, or destructively, where the amplitudes also combined but were reduced. These are water waves interfering with each other. Notice that where they are interfering constructively, it causes the amplitude to increase. You can see that in places like this. And where they're interfering destructively, their amplitudes are decreasing right next to that spot right here and here. You have destructive interference. That's interference. Recall that we also defined diffraction back then when we were looking at waves as the bending of waves when they move through an opening. In this picture, you'll see straight water waves moving from the top to the bottom. As they move through the narrow gap, the waves bend and become curved. So notice here they're straight, and when they get to this opening, they come through the opening, they're now bent or curved. If we have two gaps, that one wave that was straight becomes two waves, and guess what? Those two waves are now going to interfere with each other, and you can see the interference here. You can see this is all destructive interference through here, and through here, and through here, and through here. And then between those lines, you'll see constructive interference. This is all constructive interference, as it is in the other areas between the lines. With light waves, the diffraction nor the interference can be seen, but the effect of the light pattern the light makes on a screen can be seen. In this case, so with light, let's say these are light waves coming through the first slit marked S. And so that bends waves as they go through. And then they move through slits A and B. We get two new waves forming, and those will interfere with each other constructively and destructively. So you can see so if I had a screen where over where the other letters are, the C, D, E, F, and G are, where there is constructive interference, that would be points C, E, and G, where the waves are constructively interfering. So in other words, their amplitudes are adding up. We get bright spots. Where there's destructive interference, here at points D and F, we get dark spots, and they show up on the screen. Notice that the dark and bright spots alternate. Here's a picture of what that alternate spots would look like. Remember, we can't see any of this going on here where the interference is happening with light. This doesn't show up like it does with water, but we see this effect where you see on the screen. This can be seen happening. Here's another example of that pattern in the far right. We get bright, dark, bright, dark, bright, dark. Notice it's brighter in the center, but and then it decreases as it goes to either side. Besides bending going through a small opening, diffraction also means light diffracts going around a small object, and we can see that the diffracting pattern as light moves around the edges of this razor. Besides light, electrons also diffract. Here's electrons diffracting around a piece of aluminum. And also X-rays diffract. Here's this picture of X-ray diffraction is used to visualize molecules. X-ray diffraction has to be used for molecules because molecules are too small to be seen with a light microscope. And this happens to be the famous X-ray diffraction of DNA. It's called Photo 51, and it led to the discovery that DNA is a double helix. Perhaps you learned about this in your biology class. Let's talk about changing the subject slightly. We're going to talk about thin film interference. You've probably noticed that color in bubbles, or the color when gasoline or paint thinner is spilled on concrete. These colors are caused by interference. Thin film interference, to be more specific. The thin in the thin film is very thin, somewhere in the millionths of a meter thick. When light strikes the thin film, some light will pass through the film and refract, while some will reflect off of the surface. So if this is our incident ray going here, it hits this boundary between air and soap film. Some of it will go into the soap film and refract, and some will reflect off of it. The light that went through the film will strike the back wall, and some of that will go through and refract, and some will reflect. When the light reflected off of the back wall will travel back to the front wall, some will reflect off, that's this way, and some will go through the front wall and refract. The refraction will be in the opposite direction of the first refraction. In other words, this refraction is going to be opposite this one. So it'll wind up that the first ray that was refracted outgoing film. This means that this twice refracted may be parallel to the first reflected ray. So this first reflected ray here and this second refracted ray here are parallel to each other. But the two waves are out of phase with each other. They are off by the same distance as the thickness of the film. Here's another diagram of the same thing, but with the wavefronts painted in. Notice that there are two waves. The two waves are out of sync with each other over here on the right. These two, so the incident ray came like this. Some of it reflected off. Some of it went into the film, bounced off the back, refracted coming out, and now these two, the reflected ray and the refracted ray, are parallel to each other, but because this one, the refracted ray had to go that distance through the thin film twice, it's now off. The waves don't line up with each other anymore. They're out of phase here. So they're out of phase with each other. These light rays being out of sync with each other show up as colors. Here's some examples of light interference in nature. This is why some insects are brilliantly colored. They're not colored at all. It's the interference of the light caused by the ridges of their wings or skin. So if you look down at the bottom, the scale ridges, these these edges here cause light to reflect off of them, but that light will be out of phase with itself, and the effect is those brilliant colors. Here's some more beautiful butterflies causing the light interference within themselves because of the structure, the cellular structure of their wings. This is also why when you look at a CD or a DVD, you get that rainbow effect. And the reason for that is the CDs and DVDs encode digital information using different lengths of pits. As light strikes a pit or the non-pit area, which is called land, next to it, it causes interference, and we see this as colors. Okay, next we want to talk about scattering. I know there's been a lot of different topics in this, but we're closing out the unit, and we have a lot of things left over that we need to cover. And this one's important. The next topic we discuss is scattering. Scattering is a beam of light cannot be seen unless it's scattered by particles. This is why the sky is blue, and you want to know why the sky is blue, don't you? This picture is obviously taken on the moon. You can see the Earth in the lunar sky. It is obviously daytime because the lunar surface is all lit up. But the sky is black. Why is that? Because there is no atmosphere on the moon that's going to scatter that sunlight. Here's a picture of the sun shining on the Earth. It's obviously daytime. The sun's out. And if you look closely, you can see the Earth's atmosphere is a thin blue edge. But even in full sun, space is black because there is nothing that'll scatter the light. But on Earth, the atmosphere does scatter light, so we can see it, and it's a beautiful blue. The Earth's atmosphere is 78% nitrogen and 21% oxygen. By the way, that adds up to 99%, so we really don't need to worry about the other stuff. Oxygen and nitrogen are close to the same size, and they're both double molecules, that is, N2 and O2. So we can either imagine this as a nitrogen or an oxygen molecule, and they're close to the same size. If you look on the periodic chart, they're right next to each other. Because of the size they absorb white light from the sun and then scatter the blue away. That is why the sky is blue. So that's specifically why the sky is blue, because of the size of these two molecules. If you were to look directly at the sun, don't do it. It's very harmful to your vision. You would see it looks whitish in color. But the sky scatters the blue light around it. So where do the reds and the oranges go? And the yellows? Those colors don't scatter, so they move on. And they can be seen when the sky is very low angle, as it is during sunrise and sunset. Like this picture. Or this one. Or this one. Or this one. Did you see the green flash? That's another special effect. I'll let you look that one up on your own. This is a blood moon. It happens sometime, but why is it red? It happens during a lunar eclipse when the Earth goes in between the sun and the moon. The sunlight goes through the atmosphere of the edge of the Earth. In effect, the moon experiences every sunrise and every sunset on Earth at the same time. You might be wondering at this point why clouds are white. The sky is blue, clouds are white. Also notice lower down in this same picture that there's a haze, and that is also caused by moisture in the air. Clouds are made up of liquid water. In case you were delusional about that, thinking that it's water vapor, it's not. It's liquid water. And actually, some clouds are actually made of ice crystals. But it's not a molecular form of water. It's not H2O. These are actually very, very, very tiny water droplets. But even the tiniest water droplet is going to be bigger than an N2 molecule or an O2 molecule. The water droplets are much bigger, and they completely scatter the white light that strikes them from the sky, the sun. That's why they're white. Here, for comparison, is the sky on Mars. Mars' atmosphere is mainly carbon dioxide, and so scatters the white sunlight to this orangish red color. The last topic we want to talk about today is lasers or coherent light. So you could use those two terms synonymously, laser light or coherent light. It's the same thing. Laser is an acronym which stands for light amplification by stimulated emission of radiation. Please note that the middle letter is an S for stimulated, not a Z. Light, from most sources, is incoherent. That is, it's a combination of different wavelengths which are all traveling about on their own. There's no coordination between them. They're incoherent. Coherent light or electromagnetic waves of any kind all have the same wavelength and are aligned with each other. Lasers are coherent. That is why the light from a laser is always one specific color. Here's a comparison of incoherent and coherent light. The light from the flashlight on the left is incoherent. Different wavelengths, all doing their own thing, not interfering with each other at all. On the right is a coherent laser light, all the same wavelength, all lined up together. As you recall from chemistry, atoms have electrons in different energy levels. Electrons want to be at the lowest possible energy level, unless those levels are full, and then they'll take the next one up. If, however, you were to strike those electrons with energy packets, called photon in this picture, the electron will absorb the energy, and that means it's got higher energy, so it has to move up to a higher energy level. It is referred to in that case as an excited electron, and it can't move back to the lower energy level unless it gives up that extra energy. So it's got to lose it. It can't go back down to a lower energy level where it's preferably wants to be, unless it gives up all that extra energy that it had. The electron can lose this energy with the burst of light. The energy it gives up has to match the extra energy it picked up, and so that means it's got to be a specific wavelength or color. By the way, this is a quantum mechanical effect. More on that in our next unit. How does the laser accomplish this? Well, starting at the top and moving downwards. I know there's a lot of arrows pointing up, so that's confusing, but we're starting with the top picture and moving down. A special material or laser material is used. The first lasers used ruby. They don't have to use ruby anymore, but that was for instance, it's not a that exotic a material. Notice also that the ends are mirrors. So this end and this end is a mirror, but there's a tiny opening in this end. So yes, laser will get out. The middle part is covered up, and the laser is pumped. So we're down at the second picture. The pump is on. The pump is on. Think of this as like a light being flashed around it. The electrons of the atoms in the material will then become excited because of that light, the pumping. The electrons must give up the energy as the light of the same wavelength to fall back down to their lower energy states, which is where they want to be. The light moves back and forth with the help of the mirrors, and that'll trigger more electrons to emit excess energy. And this is referred to as a chain reaction. And eventually, light, since they're all the same material, they're all the same electrons, they're all going to have to give up the same wavelength of light. Eventually, those lights, that light will move out of that small opening, and you get laser light. Lasers have been made of many different wavelengths, depending on the material, and not all in the visible light. Only this middle portion is visible light, notice. We also have ultraviolet lasers. We also have near-infrared lasers. And by the way, they become more powerful as they become higher up in frequency. Also shorter wavelength, higher frequency, higher energy.